I'm honored to be there to share my latest research. Let me show you step by step an interpretable graph routing network or knowledge-based visual question answer. This presentation is roughly divided into 4 main sections. First, I will introduce the background and motivation of our research. Following that, I will present the methodology, the design, and experiments we conducted. Finally, I will summarize our findings and present some discussions. The task we have focused on our research is knowledge-based visual question answering. This task calls for a model to find the answer of a question by incorporating external knowledge from knowledge base beyond the content of given image and question. Therefore, the core issue of this task lies in effectively integrating external knowledge for accurate reasoning. Previous works have generally employed the strategy of encoding external knowledge and fusing it into vision language models, followed by classifying the answers based on the answer vocabulary of the training set. This approach integrates explicit knowledge from knowledge graphs with implicit knowledge from pre-trained vision language models. However, these models have limited interpretability due to their struggle to provide a reasoning process that is comprehensible to humans. Therefore, we aim to propose a method that offers better interpretability by retrieving and integrating external knowledge within a graph structure and answering questions through explicit reasoning. In this way, we can directly provide a process that is understandable to humans during the question answering process. So, in our work, we first propose a unified framework that integrates scene information from images with external knowledge from knowledge base into a unified scene knowledge graph. Then, we introduce a novel graph reasoning network, the GRN, that can explicitly reason over the scene knowledge graph for question answer, offering well interpretability. This is the overall structure of our model. In our scene knowledge graph, we fuse scene information with external knowledge. Then we select the entities mentioned in the question as the starting points for reasoning and proceeded with multi-step reasoning. During the reasoning process, we focus on different parts of the question at each step, controlling the state transitions of entities by calculating the transition probabilities of each triple path. Finally, we select the answer to the question from the entities and relationships along the reasoning path. Firstly, for the scene graph corresponding to the image, we obtain a collection of objects and retrieve the triples related to them from the knowledge base. This allows us to filter out triples that are relevant to the image. But the number of such triples is enormous, and they may not necessarily help in answering the question. Therefore, we employ an n-gram matching method to filter out triples that do not contain relationships or entities mentioned in the question. Finally, we integrate the remaining triples with the scene graph and obtain the final scene knowledge graph for this specific VQA pair. In our work, we view the reasoning process of question answering as state transitions between entities. We maintain an entity score vector and a transition matrix. At each step, it performs entity routing by transitioning the entity scores along to the transition matrix, which is computed by referencing the focused question keywords and the semantics of the knowledge graph triples. We maintain an entity score vector and the transition matrix. For the entity score vector, each entity corresponds to a dimension, and the higher the value of the corresponding dimension, the more likely the entity is to be selected as the answer, with a higher activation score. The process of entity state transition is realized through the multiplication of entity score vector and the transition matrix. The transition matrix is calculated referring to the focused question keywords and the semantic of knowledge graph triples. We represent each step's focused keywords as the weighted sum of all word vectors. We employ a pre-trained vision language model to obtain the joint embedding of the question and image, and then calculate the embedding of question keywords through a stepwise self-attention mechanism. For each triple-level pass in the scene knowledge graph, we determine the probability of the entity state transitioning along these paths in the current step by calculating the semantic similarity between the keyword vectors and the corresponding entity and relationship embedding. Gating mechanism is applied to decide whether the current keyword corresponds to an entity or a relationship. By integrating the transition probabilities of all paths between two entities, we obtain the value of the corresponding element in the transition matrix. During multi-step reasoning process, we can maintain the entity score vector at different time steps. At the same time, by integrating the activation score of relations, we can also determine the probability of each relationship being chosen as the answer. After completing the multi-step reasoning process, we select the answer from the reasoning path. Specifically, we first predict at which step the answer is located, and then we predict whether the type of the answer is a relation or an entity. Step prediction and answer type selection are achieved by calculating the weighted sum of the score vectors for entities and relations. Therefore, the model can be trained end-to-end based on labels of the answers. The training process is free from intermediate supervision signals. For the experiment, we conduct experiments on KR-VQA dataset to evaluate the effectiveness of our method. We compare our method with traditional VQA methods, knowledge integrate VQA methods based on vision language model or multimodal large language models, and scene graph-based VQA models. We found that our method can better integrate external knowledge within the scene graph, achieving excellent VQA performance while achieving good interpretability. We also evaluate the model's performance in zero-shot scenarios. Specifically, we assessed the QA pairs in the test set where the answers did not appear in the training set. Models based on classification were almost unable to answer these questions. Models based on multimodal language models also performed poorly. However, our method can handle these unseen answers very well because the GRN selects answer from the scene knowledge graph, thus having a larger answer vocabulary. In a case study, we demonstrate the interpretability of a model. By highlighting word vectors with high attention weights, we can understand which keywords in the question of the model focused on at different time steps. Additionally, we can also trace the reasoning process during the question answering by identifying triples with high activation scores during quantitative routing. So, in conclusion, we propose a novel interpretable graph routing network, which reasons the answer via step-by-step entity routing over a constructed scene knowledge graph. We ensure good interpretability in knowledge-based visual question answer, and well handle the zero-shot problem as well. Finally, we are more than happy to share some of our thoughts in the future directions of this research work. Considering future direction of the reasoning VQA framework, for better advanced scene abstraction, we are exploring improved implementations, potentially leveraging the power of multimodal large language models, which have good vision language capabilities. For knowledge integration, we aim to enhance our methodology for integrating heterogeneous knowledge into the scene knowledge graph, including open source knowledge from documents. And for reasoning, we are also hopeful that future advancements will bring forth superior algorithms for reasoning over the graph. With the advent of the large language model area, we have also developed some new insights into this research work. We believe that retrieving external knowledge in a structured form to facilitate visual question answering is promising. Structured knowledge holds certain advantage in certain object-centric VQA scenarios. Besides, explicit reasoning on graphs could potentially serve as a method of chain of thought to enable multimodal language models to provide human comprehensible reasoning process, thereby achieving model transparency. That's all for my presentation. Thanks for the valuable opportunity to share my research, and thank you all for your attention.
Okay. Let's thank the speaker.